All right. Recall that last time we talked about the CC0 machine, whose states were values like E and then an evaluation context. And we had rules like the following that said true, actually I guess I wrote false, E, where at the bottom is an if with a hole, and then ET, EF, and that this goes to EF, E. Now I talked about how this operation right here on the left-hand side is linear, because if we look at E, so E, its definition is that you either have a hole or you have an if, E, 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 or you have a sequence of values, then an E, then a sequence of E's. Now, if we were to turn these into data structures, this would be a data structure called hole that has no fields. This would be a data structure called, let's call it ifc, and it has 3 fields, an E, an E, and an E. And then this would be a data structure, let's call it appc, and it has 3 fields, one that's a list of V, one that's an E, and one that's a list of E. Okay, so then what this rule is really saying is it's saying, imagine you got a data structure, and maybe it was an appc, and then inside that was an ifc, and then inside that was another appc, and then inside that was an ifc, and inside that was a hole. What it's saying is, look at this pointer that you've been given, this one, and figure out if at the bottom is an ifc. That means it requires linear work for you to go inside of the appc, look at that E argument. Inside of the if, look at that E argument. Inside of the appc, look at that E argument. Inside of that, and find the ifc. Look inside of that and see that it's a hole. Once you realize that at the very bottom there's an ifc with a hole, only then can you know what you're supposed to do with this false. So that means that you have to go down to the bottom of it in a linear fashion. Then on the right-hand side, notice that we only have E over there. So that means we have to take this data structure and turn it into this one, where we have an appc, it's the same kind of thing, an ifc, an appc, and then a hole. So these components right here are removed. But because we're writing this down in math, this is a purely functional operation, which means that we have to actually construct an entirely new appc node, new ifc node, new appc node, and then have the hole inside of it. So what that means is that constructing this right-hand side also takes linear time. So we motivated the goal of switching to the machine model so that we could remove these linear steps, but we actually just have them back in an all different form. However, one thing that you should realize, I hope, is that there's a special data structure that we can use for dealing with values that are interesting at the, there's a structure which is optimized for when we want to look at the very bottom thing. And that is, of course, a stack. And so what a stack would do is a stack would not store this with the appc on the outside and then the ifc, then the appc, then the ifc, but in the other direction. So we would change it so that we would actually be looking at the if at the very beginning. And we can write that down in math in the following way. We can create a structure that we call the K structure. And the K structure has 3 different versions. There's what we write as K-ret, which has no pieces. There's K-if, that has an E, and a K. Then there is K-app, which has a sequence of V's, it has a sequence of E's, and it has a K. All right? We'll make a new machine that's called the CK machine, whose states are a combination of an E and a K. And now let's walk through what the different steps are. So first, the inject function. So what the inject function does is it takes an E and it's going to return E kret. So kret is kind of like a hole. And then extract is only going to run on something that has a value and a kret, and it's going to return that value. All right. So now what are the rules for the CK machine? The rules for the CK machine are quite straightforward. The first rule says that if we have an if, EC, ET, EF, and some K component, then what we do is we focus on the EC and we construct a KIF with ET, EF, and the K. Notice that this is a linear amount of work, a constant amount of work, because we can immediately look at something and tell whether it's an if. And then what we do is we just create a constant new KIF structure on the outside. Then if we have a false, and at the top of the K is a KIF with ET, EF, and K, then we reduce this to EF, just the K, just that K right there. Notice that this takes constant time because we can immediately look at that K component and just tell what it is and return the appropriate thing. Next, if there's a V here, KIF, ET, EF, K, then we would just return ET, K. So again, constant work. Next, what if there's an application? If there's an application, then we have E0, EM, ... K. This will get turned into the following. E0, then we have a K app with no values, then the sequence EM, and then the K. Next, if we have V1, and then a K app, where we have V0, ... E0, EM, ... K, then we're going to turn this into that E0 right there, and then a K app. Now here's a little bit of a trick. If we write V0 ... V1, then that means that it takes a linear amount of time because we have to store it at the end. So what we're going to do is we're going to store this list backwards. So we're going to write V1, V0, ... EM, ... K. Next, we only have one more rule, and that's going to say that if we have Vn and then a K app of V0, ... and then there's no more expressions, and then a K, then we'll turn this into delta of V0, ... Vn. Actually, you know what? Let's write that slightly differently. Let's say that we'll reverse Vn, V0, ... Okay. Now technically that takes linear time, but we can also do another trick. Maybe what we could do is we could make it so that our delta function expects the things in the reverse order. So this system now is made up of entirely constant steps at every turn. Let's look at the evaluation of our example program. And let's label the rules again. So we've got rule 1, 2, 3, 4, 5, and 6. Okay, so we start off with plus 1 times 2, 3, and we first call inject. And we get plus 1 times 2, 3, k-ret. Okay, then we have rule 4. And rule 4 says that we have a plus, and then a k-app of nothing, and then 1 times 2, 3 as the expressions, and then k-ret. All right, then we have rule 5, where we swap out the 1 and the plus. So we have a 1 here, then a k-app with a plus, and a times 2, 3, k-ret. Then we have another rule 5, where we have times 2, 3, k-app, and then to keep this linear, to keep this constant, we have 1 plus. And then this is empty, k-ret. Now here we use rule 4 again, and we have times k-app, nothing, 2, 3, and then the other k-app from before, 1 plus, nothing, k-ret. All right. Then we have rule 5, where we swap the 2 in. So we have 2 k-app times 3. Now you may think to yourself, like, isn't it annoying that we have to go through each one of the constants? Well, there needs to be some part of our program that analyzes them and realizes that they're constants, and that's what this is doing. It's checking to make sure that everything is actually a constant. Okay, so now at this point, we have nothing in this spot right here in a value, so therefore we can actually evaluate. So then we now use rule 6, and we have delta of times 2, 3, or 6, and then we have this k component right there, k-app, 1 plus k-ret. All right. Then this is another use of rule 6. So we have delta of plus 1, 6, or 7, and we have that, which is k-ret, and then we use extract, and we get the answer out, which is 7. Now, one thing that you'll notice is that there's exactly the same number of steps as in the CC machine, except that now every step takes constant time. This right here is the traditional CK machine. Now there's a few things to comment on about the CK machine. The first thing is that notice that the K component is like a stack, where the values on the stack are either ifs or apps. So we could say that K is equal to a stack of frames where a frame is either an if that has an E and an E, or it's an app that has a sequence of values and a sequence of expressions. Okay? And what we do is we push things onto the stack, or we pop them off, or we inspect the first thing, which really just means that we're going to pull something off, inspect it, and then push it back on. In programming languages, like C and whatnot, they are implemented exactly like this. And the stack in your program serves the exact same purpose. In programming language, though, we don't call K the stack, we call K the continuation. So K is called a continuation. And why is this? Basically, the idea is that a stack is an implementation technique, and a continuation is an abstract idea that is more general than just a particular way to possibly implement it. In particular, notice that the way that I've written it here, it's not literally a stack, it's actually a data structure that has a stack-like usage, because each frame, each K variant, has a pointer to another K inside of it. So that means it's kind of like a stack, but it's not literally a stack. Now, the reason it's called a continuation is because what the K component does is it describes what will happen after part of the computation is over. So for instance, I could look at something like this 2 right here, and I can say, what happens after the 2? And the thing that happens after the 2 is that it gets multiplied by 3, and then that gets added to 1, and then we return. So I can look at the continuation and figure out what's going to happen after this part of the program is over. Now, many novice programmers believe that the stack describes what happened in the past of a program. So novices think the stack is the past of a computation. But it isn't. The stack tells you what will happen after a program is over. So consider a C program, for instance. Imagine you have a C program, and you look at the stack, and it says, well, there's F on the stack, and then G on the stack, and then H on the stack, and then this is where I am right now. Now you may say to yourself, well, this means that I used to be inside of the function H, then I used to be inside of the function G, then I used to be inside of the function F. And that's kind of true. The problem is that what if your program looked like this? What if your program, if inside of the function f, it said something like x equals calling the function a, and then x equals calling the function g, and then we're going to return x. And then inside of g, it says y equals calling the function b, and then y equals calling the function h, and then we're going to return y. And then inside of the function h, that's what's happening right there. Notice that the past, if we look at your computation as a graph, it looked like this. First, we started in f, and then we went down here to a, and then we went back to f, and then down again to g, and then we went down to b, and then we went back up and over to h, and then that's where we are right now. And then when we're done, what's going to happen is that we're going to go back to h, and then we're going to go back to g, and then we're going to go back to f, and then we're going to be done. Notice that the past of our computation includes a and b, but they are not represented in the stack. The stack only tells us what's going to happen after this is done. After it's done, we're going to return to h, and then after that, we're going to return to g, and then after that, we're going to return to f. So the stack, it only shows you the past in as much as the past is often part of your future, because it's very common in programming languages to call a function and then do something with the value, like maybe we'll add 1 here and we'll add 2 there or something like that. Okay? So because the past often influences the future, that's why the stack appears to have components of the past in it. But really, what the stack is doing is it's keeping track of the future of your computation. And this is actually quite significant. All right. The next thing that I'd like to do is talk about how to implement the CK machine really, really concretely. So imagine that we want to write down a little while loop that is the CK machine. Okay, so that means that CK is going to be a function that takes in an e and returns a value. All right? And here's how it's going to work. It's going to do something like this. It's going to say the C component sorry, we'll say that, yeah, ck e, and we'll say it's going to return a v. Okay, so we're going to say that there's a variable called c that equals e, and there's a variable called k that equals a new kret. And then what we're going to do is we're going to say, while 1, so we're just going to do an infinite loop, we're going to say case of c. All right? Now, if we get an if, then we're going to get an if with an EC, an ET, and an EF. And this is going to correspond to rule 1 of the CK machine. So what we're going to do is we're going to say that C is going to equal EC, and K is going to equal KF of ET, EF, and K. And then we're going to go back to the top of the while. And then if instead we got an application, and an application has a sequence of E's, okay? And that sequence of E's, let me just clear this up a little bit. That sequence of E's has an E0 at the top and then some more E's after it. Then what we're going to do is we're going to say that C equals E0 and K equals K-app of the empty list, which we'll write as brackets, and then the E's, and then K. And then if it's not an if and it's not an application, then that means it must be a value. So if it's a value, then at that point what we want to do is we want to inspect K. So then we'll say case of K. And if it's a kret, then what we'll do is we'll return v, and that's the extract function. We're done. If instead we got a kif of et, ef, and k, then what we need to do there is we need to say c equals v question mark et, ef, and k equals we'll call this k prime. K equals k prime. All right. Then if we got a k app, that means that we have some values, some expressions, and some inner k. And what do we do in this case? What we do in this case is we're going to do a case on e's, and if we got an empty list, then what we want to do is we want to say that C equals delta of reverse of V, that's this V, put on to V's, and then K equals K prime. And if it's not a reverse, if it's not empty, then that means that there was at least one thing inside of there, in which case we'll say that C equals that first thing, and then K is going to equal K-app of sticking this V on top of the list, and then leaving these things alone, and then having K prime inside of there. This right here is the entire CK machine written in basically, code that's like C. So your CK machine has one argument expression and it returns a value. It has two variables, C and K. It has a while loop, and the first thing you do is you case on C. Now, you may think, well, how do I case on C in a language like C? Well, what you would do is you would do like a switch statement, right? And you would look at a field of the C component. Like one thing that you could do is you could make it so that there's like a union that is all of your C data structures, and then there's a value that's outside of the union of the struct that has all of them. What I mean is this. What I mean is that we could define a struct for code that had like an integer for the type, and then that would be things like 0 for a number, 1 for a bool, 2 for an if, 3 for an app, and so on. And then there would be a union where there would be a struct for numbers, and that would have a number in it. And then there would be a struct for ifs, and that would have 2 codes in it. Maybe they would be code pointers for the condition, another one for the true side, another one for the false side, and so on. So this would be a way of encoding it. That's, of course, in like bare C. Obviously, if you use C++ or Java, it would be easier to do a case statement like this. And notice that what each side does is all you do is you check to see what the case is, and you just update the two variables. So you just update C and K, update C and K. If it's a value, you look at K now, and you either return it or update C and K, or check out E's and update C and K. So notice that this C program, this implementation of the CK machine, is extremely trivial. In fact, it's so trivial that you could quite easily write it directly in, low-level C or assembly even, and that's actually the whole value of the CK machine. The CK machine lends itself very easily to implementations like this. Now, the last thing that I want to mention is that in the assignment, I highly recommend that you structure your code in the following way. I highly recommend that you write your CK function in C or maybe C++ if you prefer that. And then what I suggest that you do, and we're going to call this your low-level program. I suggest that you also have a high-level program, and maybe you'd write this in like Racket or Python or JavaScript or something like that. And what you want to do is you want to have functions like desugar in the high-level language. Then what you want to do is you want to have some way of having it so that your high-level language can generate programs in your low-level language. Here's the way that mine works. In my high-level program, I have a function that's called check, and it would take as an argument the string +1 times 2, 3. And it would also have the number 7. Really would have the string 7. Then what happens is my high-level language is going to take this and it's going to turn it into a file that's called x.c. And if I go look inside of x.c, it looks like this. It looks like include low-level.c. Then it says int main. Then it says ck. And then it says make app. And then after it says make app, then it says make primitive plus. It turns it to the symbol plus. Then it says make number 1. Then it says make app. Then inside there it says make prim molt. And then make number 2. And then make number 3. Then we close the app. Then we close the next app. Then we close the CK. Then we close the brace. And then we're done. And so that's what my x.c program is. Then, after check makes that program, then what it does is it calls the C compiler on xc, and it outputs x.bin. Then what it does is it runs x.bin, and it puts the output into x.out. And then what it does is it reads x.out, and it gets an answer, let's say 7. And then what it does is it compares that up with this, and it sees if it's the same thing. If it is, then it returns true. And if it wasn't, then it would error. And so now what I can do is I can have my high-level program implement my reader, my desugarer, all the other things that we'll talk about in the class, and I can do that in the pleasant language that I like using, because I don't like writing C programs. So I can write it in this pleasant language that I prefer to use, but then I can write my low-level C program in a really simple language for writing the CK machine. I highly recommend that you structure your code this way. I think that really the only time that you wouldn't want to do this might be is if you are really comfortable with C++ as your high-level language anyways, and you want to do that. But it may, even if you use C++, it may be convenient for you to even have this structure where you have two separate programs. All right, so that is all for today.